Okay, so now see, the silanes have the highest rate of hydrolysis. So if you look at this here, so you could carry out similar hydrolysis with germanes, tannins and plumbases also with NaOH. But for silanes, just with water, you see that the hydrolysis is taking place and hydrogen gas is given out. Alright? Yeah. Now, this, the length of the chains that are there is of course for hydrocarbons, it is enormous. In fact, hydrocarbons show great degree of catenation. What is catenation? What is catenation? The ability of an atom to bond to another atom of the same type. So you know, in these carbon fibers you have 20,000 carbons that have bonded together to form long giant polymeric chains. All these polymers, many of them are carbon polymers, and then the degree of catenation decreases from carbon to silicon. So silicon, only 6 silicons can form long chains, and germanium also 6 germaniums can form long chains, and lead and tin catenation not really observed. So long chains formed for carbon, and then for germanium and tin it rapidly decreases to 6 and 6. Now the reason for this is the bond strength. So silicon, carbon has great carbon-carbon bond strength. Bond strength is very high. Okay, the bond strength for silicon, germanium rapidly decreases because of bond length increases, bond strength decreases, and there is another reason for that, and which is that the metal hydrogen bonds, or the metal, whatever, maybe there's a chlorine or fluorine attached or an oxygen attached. In the case of a carbon chain, the carbon-carbon bond strength is almost the same as a carbon-hydrogen bond length, approximately. Yes, so that makes the chain strong. Whereas for silicon and germanium compounds, the metal-metal bond strength becomes weaker than the metal and the other atom that is attached to the chain. So that makes this whole compound extremely unstable, right? So the reason that, what is the reason here? That the carbon-carbon bond strength is almost the same as a carbon-hydrogen or a carbon-chlorine, right? Now there is another reason also for that, which is that in the case of carbon, all 4 bonds are used up, right? There are 4 electrons and 4 bonds, and there are no empty d subshells and no lone pairs, right? What are the 2 factors? No empty d subshell, no lone pairs. That makes the carbon-carbon chain strong and durable, right? The presence of empty shells takes away electrons from the chain and makes the whole thing unstable. So, to recapitulate, why do carbons form long chains and it rapidly decreases for silicon and germanium? Tin and lead don't show at all. What is the reason? First is the metal-metal forms strong bonds in the case of carbon, central atom. Carbon-carbon forms strong bonds and as strong as the element attached to it. What is the second reason for that? No empty d subshell, no lone pairs, and that makes the whole compound very stable. This fact, this ability to show catenation is marked in carbon compounds, not so much for germanium, tin and lead. So for carbon, the length of chain is enormous, big, 20 and beyond, right? For silicon and germanium, only 6 and 6 silicon bonds, right? This is reflected in the also in the stability of the hydrides, as we've just studied it. So we've done the hydrides. Next we go to the oxides. Okay, so now oxides of the group. So they all form monooxides and dioxides. Okay, they all form monooxides and dioxide. So the monooxides first, oxides of the group. Monooxide is carbon monoxide, silicon monoxide, germanium monoxide, tin monoxide and lead monoxide. Lead monoxide. Carbon monoxide and silicon monoxide are neutral, and these three are increasingly more and more basic, but in truth they are, we've written it as basic, but we'll be studying these properties in some detail, and you will see that these are actually show some degree of amphoteric character. Alright, now carbon monoxide preparation we will be doing subsequently. We have to study this in detail. Silicon monoxide may be prepared by silicon monoxide, just taking silicon dioxide, adding silicon and heating it to 2300 degrees centigrade, and this becomes 2 times silicon monoxide. Okay, germanium monoxide prepared by taking germanium chloride using valency 2 of germanium, right? GeCl2 plus 2 times HOH, giving you GeOH whole twice plus 2 times HCl, right? So this even at room temperature, slight warming, this reaction will occur, and then this is a yellow colored compound and this is a precipitate. This germanium hydroxide may be heated to around 600 degrees centigrade to give germanium oxide and water. To give germanium oxide and water. So this is germanium oxide. Okay. SnCl2. Now we are trying to prepare stannous oxide. So you have to take SnCl2, 2 times NaOH, giving you SnOH whole twice plus 2 NaCl. Okay. Now SnOH whole twice, just on heating, gives you stannous oxide and water. Okay. So see, preparation of this is the most difficult because you're trying to get valency 2, which is the inert pair effect, of course, becomes more apparent as you go down the group. Isn't that right? Okay. And lead. Lead, you know, valency 2 is the most stable. You have to do nothing to it. You just have to take lead, heat it in air, and you will get litharge pumice oxide. Okay. So these are the monooxides, right? Now we come to the dioxide. So the dioxide, all form the dioxides. You do remember, of course, that silicon monoxide is unstable, right? Carbon monoxide is very stable, you know that, because it's got the 3 bonds between the carbon and oxygen, and the bond order is high. So carbon monoxide is very stable, forms so many coordinate complexes. Silicon monoxide is unstable, and the stability of the monoxide would of course increase down the group. So PbO is very stable. By direct synthesis you can get it. Now carbon dioxide, the dioxides, that is the dioxides. So you have carbon dioxide, silicon dioxide, germanium dioxide, stannic oxide and plumbic oxide. Okay, now these two are acidic and these are amphoteric. Okay, do you remember that when you use the higher valency of the metal, its oxides tend to become acidic or amphoteric, right? So like you have Mn2O7, that with water will produce a permanganate ion, or with NaOH will produce the permanganate ion. So same is true here. You've used the higher valency and the whole oxides have gone towards the acidic or amphoteric types. Okay, right. So this then, so much about the general oxides of the group. Right? Now, right. Now, next we go to carbon. Allotropes of carbon. So this entire group shows allotropic modification except for lead. Lead has no allotropes. Now we look at carbon in particular and some compounds of carbon. And some compounds of carbon. Okay. Now, the crystalline allotropic modification of carbon is of course diamond, and every carbon is attached to 4 other carbons. Every carbon is sp3 hybridized, alright, and the bond angle is exactly 109 degrees 28 minutes. Okay, right. Now, so this is a giant polymeric molecule. This is diamond, and you have carbon, and here it carries on this way, right? Now the bond length of the carbon-carbon bond length here is 1.54 angstroms. Okay, and in the case of graphite, the carbons are sp2 hybridized. Okay, and it is here flat planar structure, and it will carry on in this fashion. Like this. Here, right? And alternate single and double bonds. Yeah, so you can see these are conjugated systems like this, and this will, by resonance, the double bonds will also form partially between this carbon, and so on and so forth. Alright, now the bond length, the carbon-carbon bond length, which has a partial double bond character, is 1.42 angstroms, right? And between one such layer and the second layer, there are van der Waals forces of attraction. Yes, and the distance between one layer of graphite and another layer of such flat planar graphite is 3.4 angstroms. Yes, and the reason is that there are van der Waals forces that exist between two such layers. These forces are weaker. Now you notice that the bond length in diamond is bigger than graphite. Alright, and that is because in the plane the graphite has partial double bond character between every carbon. Partial double bond character between every carbon is there for graphite. Graphite, of course, now density of diamond is 3.5 gram per ml and density of graphite is 2.25 gram per ml. Density. So, of course, diamond is a hard substance. Graphite, although the bonds are shorter, stronger, but between two successive layers, there is a lot of space and that has decreased the density a lot. Okay, so now graphite can be powdered because although the bonds are very strong, it is only one atom thick. Each layer is only one atom thick, right? So, when you hammer it, these layers break easily and they break into smaller and smaller pieces and ultimately become a powder, and graphite may be used as a lubricant in parts of machinery exposed to high temperature, because there you can't use grease because the grease is inflammable, will start to burn out, right? So graphite may be used as a lubricant and this. Of course, diamond has very high refractive index, 2.5, right? This refractive index of diamond 2.5. Right? So when you in a crystal of diamond, when a ray of light enters it, it undergoes multiple total internal reflection, bouncing about inside the crystal, giving it that glitter, no, that shine peculiar to diamond. All right. The thermal conductivity of diamond is more than graphite. But electrical conductivity of diamond is an insulator. It doesn't conduct electricity. Graphite conducts electricity because these pi electrons are loosely held. So it will conduct electricity in the plane, but not across planes. This property is called anisotropy. Anisotropy. Anisotropy means, different properties in different direction. In the same crystal, in one direction you have a certain magnitude of a physical property, and in another direction you have another magnitude. So this is anisotropy, where in this direction it is a non-conductor, but in this direction it is a good conductor of electricity. Yeah. So now in solid state we will be doing the crystal structure, and here we just give it to you but discuss it later in detail when we do the chapter of solid state. Yes, and the crystal of diamond is like the zinc sulfide crystal. You can just write that down. The crystal of diamond is like the zinc sulfide crystal. It's like the ZNS crystal with carbons occupying the corners and face centers of a CCP lattice. Diamond, okay, carbon atoms at the face center six faces and corners, 8 corners. In addition, at the alternate positions of tetrahedral words. So covered when we do solid state. I've just given it to you here since it's relevant, but we will not go into any details here. So this then is diamond. Alright? Okay. So now you have amorphous allotropes also. You have coal, coke, then you have the different forms of coal are there. Most the pure form is anthracite. Okay. Then right now reactions of carbon. Carbon reacts. Three categories of reactions of carbon are there. One is reaction of carbon with certain oxides. Okay, so you have reactions of carbon. Okay, so you have Fe2O3 reacting with carbon when heated. You have Al2O3 reacting with carbon also on heating. You have water, steam passed over a bed of red hot carbon. Okay, so all three reactions are a little different. This will give you 2 times iron plus 3 times carbon monoxide. Okay, this gives you Al4C3 and 9 times carbon monoxide. This of course gives you hydrogen gas and carbon monoxide. This mixture is called water gas. Okay, so this is carbon reacting with all these different things. This is a methanide. Aluminium carbide. This is a methanide because it produces methane with water. And this here is used for the extraction of iron. Okay. Then you also have barium sulfate. Barium sulfate reacting with carbon on heating, and see it becomes barium sulfide. So sulfur from +6 has gone to -2, undergone reduction, +4 times carbon monoxide has gone. Then you can have calcium oxide reacting with carbon. Now this we have done in group 2. Recall that this gives calcium carbide plus carbon monoxide. This is of course an acetylide, because see, this with water will give you methane. This we've done in group 3, and this with water will give you acetylene. So this is calcium carbide or calcium acetylide. Calcium carbide or calcium acetylide. Right? Okay, so we've got this then. Right? Okay. So this is the reaction of carbon with all these different compounds. Calcium will also react with the oxo acids. Yes? So with HNO3, H2SO4. So reaction of carbon with oxo acids. So you know you have 2 HNO3 concentrated and heated, giving you water 2NO2 plus O. If you multiply this by 2, both these oxygens with carbon will give you carbon dioxide. Yeah. And so if you add it up, is carbon plus 4 times HNO3 concentrated and heated, giving you 2 times water, 4 times NO2 and CO2. So here this carbon, the element carbon with nitric acid concentrated and heated is giving you 2 gases, the reddish brown nitrogen dioxide and also carbon dioxide. Similarly, sulfuric acid with carbon. Now you know how sulfuric acid H2SO4 with carbon will give you carbon dioxide, sulfur dioxide and water. Right? Now see, see, you can do it by this half reaction method. What is that method? H2SO4 giving you H2O, SO2 and O. You would have to multiply this by 2 and get the carbon to react with that oxygen. Or otherwise you do it directly by charge balancing. How would you do that? This is plus 6 gone to plus 4. Right? And in the process it has taken 2 electrons. Carbon gone from 0 to plus 4 and in the process given 4 electrons. So clearly you need 2 of this to give you 2 SO2 and the electrons are balanced, and then the rest is of course just 2 times water. Alright, so here you have carbon with nitric acid or carbon with sulfuric acid giving you CO2 and SO2. Okay.